our, say, current in this circuit will have this form. So at the moment, the only unknowns are the amplitude and the phase. We know that it will have the same frequency, and it will be exponentially decaying with the same damping factor. These cannot change. The circuit cannot change these, because the circuit is linear. Okay? If the circuit is non-linear, that would be different. But then it would be extremely difficult to deal with. It can be done, but not at this stage. And usually, nowadays, it's not done by hand anyway. So how do we calculate the response of that circuit? How do we find IM and phi? Well, first we look at, we can express the forcing function, or just the real part, as a real part of a complex function. When instead of cos here, we have this j omega t plus phase, okay, which was 10. So this is the forcing function, can be expressed like that. So that's the Euler's, we use here Euler's formula, when the cos function is expressed as a sum of exponential functions with the imaginary exponent. Take just a real part, and this is exactly what our forcing function looks like. So we can rewrite it in this way. So because the V is the phasor, as the magnitude phase, and S now is a complex frequency. It has real part, which is the exponent of that, or the coefficient of the damping factor at the exponent, and the imaginary part, which is the omega, the frequency. So then we write KVL around the loop. So just adding voltages across all three components goes to the forcing voltage. Substitute a complex forcing function, and assuming complex force response, we can express this equation like this. Okay. Now we can divide by the common factor, E to ST, and we have a simple phasor expression. So all we do is just take out I outside and divide by whatever is in the brackets. Okay, so we found a phasor expression for the current. So what we do, how do we solve it? Well, we know S. S now is a complex number. Previously we used j omega only, but because we didn't have exponential factors. We didn't say that then, but now we introduce an extra additional function into it. So when we put S as minus 2 plus J4, we can solve it, okay? And we get the normal phasor expression for the current. So we have its magnitude, and we have the angle. So we can easily now write down the response in time domain. So let's just introduce something that will even more simplify the analysis. Okay, so we introduce so-called generalized impedance and admittance. We already know what impedance and admittance is. We define it first as for purely sinusoidal signals. Okay, but now we have a signal that can have this exponential decay. So we redefine impedance and admittance. It won't be really much different, as you will see in a moment. So we know that voltage current relationship on an inductor, which is V equals L di dt. So if we apply complex voltage and current equations for it, we get this expression, when V and I are phasors, of course. So taking derivative will give us next equation, then again getting rid of e to st or cancelling e to st on both sides, we get this, which is something we already seen, okay? We have V equals SL times I. So V is voltage, I is current, so SL must be massive units of resistance, which we call impedance here. So we've seen that already, except that now S may be not just j omega, not purely imaginary, but it may be a complex number. And the same thing, of course, will happen. So this is just a description in time domain and frequency domain. And the same will happen to the other component, the reactive component, which is capacitor. So we have its impedance as 1 over SC. And resistor, of course, doesn't change in the frequency domain. So let's just redo that example. Now, without going into the differential equations, we simply apply the phasor voltage, and since there was an exponential decay, the only difference here is that S, instead of being purely imaginary, is now complex. So that exponential decay added just the real part of the complex frequency, and it's -2. Apart of that, nothing has changed. You should know how to analyze circuits like that. You simply calculate total impedance, which is the sum of impedances, when S, of course, is no longer just j omega, but it's sigma plus j omega, and do the calculations. And knowing that the damping coefficient cannot change, so if it was -2, in the response will also be -2. And omega will also cannot change, so it will be 4. So we can very easily go back to the time domain from this simple phasor expression. So all you need to know is the phasor expression, which gives you magnitude and the phase, and you need to know S. So you can, using S, you can recreate the time domain damping factor and exponential decay and frequency. So that's what this complex frequency is. It's not. It's